base, collector, the emitter, and it comes in a package that looks like this. Now, you need to get this in your breadboard with the proper orientation. I've known many students who spent their 3-hour time block in lab with the transistor in backwards. It won't work backwards. You've got to get it in there correct. So you grab it by its 3 little feet, hold it up so that you can read 2N3904, and from left to right, it's emitter, base, collector, like a sum mnemonic. Such as even brewer can. Make up one of your own, but don't get it confused. You've got to get it in the breadboard with the correct orientation. And this is a discrete transistor. Now, if we were to take a single transistor, an NPN BJT, define the collector voltage as the output. The input voltage to be the voltage connected to resistor RB in series with the base. And we have a DC power supply, B plus up here, which simply means we've got a battery here connected to this point, which has a value of B plus. It's the positive power supply. It's normally not drawn in, just for simplicity purposes. If we plot V sub O versus V sub I, as V sub I varies from 0 to the positive power supply voltage, what we'll find is V sub I is less than or equal to V gamma, where V gamma is the turn-on voltage for the transistor. If V sub I is less than V gamma, the base emitter junction is off. It doesn't turn on until the base emitter voltage has a value of about V gamma volts, which has a value of around 0.65 volts. Some people use 0.7 volts. But for the type of transistor you're going to be using, it'll be 0.65 volts. So if the transistor is off, the currents in all 3 of the terminals are 0. So if the currents are 0, as long as V sub I is less than V gamma, then the output voltage, V sub O, is given by V plus minus IC times RC. So if the transistor is off, if V sub I is less than V gamma, the output voltage is equal to V plus and V sub I is equal to V gamma. Once V sub I is greater than V gamma, but less than a certain voltage, which we'll discuss in a second, the base current is given by V sub I minus V gamma divided by RV. And another symbol I could use for V gamma is simply the DC voltage from base to emitter. We'll switch over to that. We've got a linear relationship between the input voltage and the base current. The collector current is equal to beta times the base current is we've got a linear relationship between the output voltage and the input voltage. We've got a straight line with a slope of minus RC over RB until the input voltage reaches a value so that the output voltage is equal to a voltage called the collector to emitter saturation voltage, which is a small voltage which has its value of about 0.2 of a volt. Then, as we increase the input voltage, the output voltage stays at ECE sat. So, if we want to use this transistor as a switch in a digital electronic circuit, we'd be interested in two nonlinear regions for V sub I is less than V gamma, or V sub I is greater than this value, which causes the transistor to go into saturation. We want an amplifier, we want to be in this region. So this is a linear region. These two are nonlinear. Later on in the semester, we'll be looking at the transistor as a switch. We'll be interested in the nonlinear regions. But for experiment 1, we want to design an amplifier. And our input source, instead of a variable DC voltage, is going to be some kind of time-varying voltage as a function of time, like you might find at the output of a microphone. Well, if you were to connect a microphone up here, it would bias the thing. But we would like to make the bias somewhat independent. We like the bias to be somewhat independent of the DC voltages on the transistor. If we were to connect a speaker up to the collector terminal at the output voltage, we'd have a DC current flowing through the terminals of the speaker, which would cause the tone to go all the way on one side. So if we want an amplifier, we want to add some components to this. To get the circuit that we're going to be looking at, the common emitter amplifier. So, we have the resistor RC in series with the collector, connected to the positive power supply voltage, the transistor, and now we're going to put a resistor, RE1 here, to stabilize the operating point, the DC operating point of the transistor, make it independent of slight variations in the base emitter voltage. We're going to set the DC base voltage with two resistors, RB1, RB2, with positive power supply up here. Then, if we want to keep a DC voltage or current from going through the signal source, we put a capacitor here called a coupled capacitor. Its only purpose is to block DC. Then, if we want to keep DC off the load, we put another coupled capacitor here. We put our load resistor here. And this is the output voltage. Now, if we leave this resistor, RE1 here, which is called an emitter degeneration resistor, it will greatly decrease the gain of the circuit. And so in order to come up with a gain, which will be independent of the biasing of the circuit, we put another capacitor here, C sub E, and a resistor, RE2. Now, we come to homework problem 1, which says we want to